In section 2.4, I'm going to discuss some of the important patterns that we can see in uniformly accelerated motion. To start with, I'm going to mention an experiment performed by Galileo Galilei in the 16th century. In it, he worked out the mathematical patterns that we're going to discuss here. In his experiment, he used several bells set up on a ramp that's shown here, and he would roll a ball down the ramp, and he could adjust the location of the bells. And what he did was he adjusted the location so that they would ring at a regular rate. Galileo was trained in his early life as a musician, so he was really good at keeping a beat. Galileo didn't have access to things like meter sticks and stopwatches, and so all of the measurements that he made were in proportional terms. He was able to measure a distance and then a different distance, and then compare the two in a proportion. And what he found was that when he set up the bells in a pattern that the bells would ring at a regular rate. Uh, he saw that if he measured the distance from the top of the ramp to the first bell and then the second bell, he found that those two distances had a ratio of 3 to 1. And he found that the distance from the second bell to the third bell was 5 times the distance from the top of the ramp to the first bell. And then the next one was 7 times, the next bell 9 times. And then to the very bottom of the ramp, which would also make a sound, was 11 times. And hopefully you can see the pattern here. These are all the odd numbers. And Galileo called this the odd number rule. In a given time period, in equal time periods, the distance traveled by the rolling ball followed the pattern of 1, 3, 5, 7, 9, and 11. That pattern is actually indicative of a bigger, more general pattern. If instead of counting the distance between individual bells, if he measured the distance from the top of the ramp, well, the first bell is obviously 1 unit, but how far is the second bell? Well, 1 plus 3 is 4 units. Well, how far is the third bell? Well, 4 plus 5 is 9 units. And what's the next one? 16, 25. And the last one would be 25 plus 11 is 36. And hopefully you see the pattern in those numbers, right? 1, 4, 9, 25, 36. These are all the perfect squares, right? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And so Galileo saw that there was a pattern that the distance traveled divided by the time squared is going to be a constant. And that is an important pattern. We see that pop up for all objects undergoing uniformly accelerated motion. That the distance traveled, if it starts from rest, is proportional to time squared, and that's an important pattern to see. And here it is summed up that at any given time, you can see that the distance traveled follows the odd number rule 1, 3, 5, 7, and then the total distance here is follows the perfect squares 1, 4, 9, 16. And that shows the underlying relationship between the distance and time for a uniformly accelerated ball rolling down a ramp. So on this slide, I'm going to discuss some of the important details. The first that we're going to look at is the relationship between speed and time. Now, I'm going to discuss this specifically from an object that is beginning at rest. So this pattern does not hold for objects that don't start from rest. So if the initial speed is 0, that term drops out and we just get a times t. And you should notice that this fits the pattern for a directly proportional relationship. where we have y equals some constant. Remember, the acceleration is a constant for uniformly accelerated motion times x. And so this shows that the velocity is directly proportional to the time. And again, this is only if the initial speed and the initial velocity is zero. Only if the object begins from rest. Now, what about the distance or displacement? So here's the equation for displacement as a function of time. And again, we're going to concentrate only if the initial velocity is zero. If the initial velocity is zero, that term drops out. And this is what we have left over. And what we should notice is that on t, one of our variables, we have t squared. And what that's going to tell us is this fits the pattern for a square relationship, which shows that displacement is proportional to time squared. And this is what Galileo showed in his ramp experiment. And in his ramp experiment, the initial speed was zero. He was dropping the ball from rest at the top of the ramp. And the last one that we can see is what's the pattern between speed and distance. And again, we're looking at this from a perspective where the initial speed is zero, where it starts from rest. In this case, this is what we have left over. And we should notice that our two variables, speed and distance, speed has an exponent of 2, and distance or displacement has an exponent of 1. And that fits the pattern for a square root relationship, where it's the speed squared that's proportional to distance. Or an alternate way to say that is speed is proportional to the square root of the distance. Both of these statements are saying the same thing. They are mathematically identical. In this example, a student releases a marble from the top of a ramp so that the marble rolls 100 meters before hitting a stopper in 4 seconds. And part A wants us to calculate the marble's speed when it hits the stopper. We'll start the problem off by identifying the given and unknown information and making a given and unknowns table. So it says that the student releases a marble. That is going to imply that the initial speed is zero. So we'll put that down in our givens and unknown table. From the top of the ramp so that the marble rolls 100 centimeters. 100 centimeters is a distance. I can identify that as a distance because it has units of length, and units of length correspond to a distance or displacement. Before hitting a stopper in 4 seconds. So 4 seconds, seconds is a unit of time, so that's giving us the time. And part A wants to know the marble's speed when it hits the stopper. So that would be a final speed. That's our unknown. So the equation that contains the final speed is the average speed rule. I'm allowed to use it because when the marble is rolling, it is steadily changing its speed. It is undergoing uniformly accelerated motion. The initial speed is zero, so that goes away. And if I multiply each side by 2, that will eliminate the 2 from this side, leaving SF by itself. And on the other side, we'll have 2 times the average speed. So to find the final speed, I will need to determine what that average speed is. I'll do that down here. Average speed is also distance over time. I'm given the distance, I'm given the time, so I can just plug those numbers in. And 100 over 4 is 25 centimeters over seconds, gives us units of centimeters per second. I can then take this value and put it in up here. And the final speed of the marble, 2 times 25 gives 50. Don't forget units, centimeters per second. As a continuation of the last example, here we have a student that releases the same marble on the same ramp. So that phrase right there, that's going to indicate that the acceleration for this second roll is the same as on the first roll. But this time, the student releases the marble higher up on the ramp so that it rolls 400 centimeters, which is a distance, before hitting the stopper. And part B wants to know what's the marble's speed. So this is asking us to calculate a speed. And part C wants to know how long does it take. So this is asking us to calculate a time. Now, you could absolutely use the UAM equations and find the acceleration, and then use that to solve B and C in sort of a plug and chug type approach. But if we notice that there's a straightforward relationship between speed and distance and time and distance for a uniformly accelerated object, well, we can set up a scaling equation. So we want to look for an equation that has speed and distance in it. The positive physics set of equations does not have this type of equation. So we're going to have to use the UAM equations to solve for this. So we can get rid of this term with V initial in it. And we should notice that since the acceleration is the same, this term, or this coefficient rather, 2a is a constant number. And so the final velocity or final speed is going to equal a constant number, k, times delta x. And this is going to imply that we have a square relationship where it's the speed squared, velocity and speed are the same thing, that's proportional to the distance. Displacement and distance are the same thing for straight line, one-dimensional motion. And so now we can use this relationship to set up a scaling equation where the ratio of speeds squared is equal to the ratio of distances. In this continuation example, we have a student that releases the same marble. Because it is being released, that's indicating that the initial speed is 0. The same marble on the same ramp. So that's indicating that on the two rolls that the acceleration is the same value. But this time higher up the ramp so that it rolls 400 centimeters before hitting the stopper. So that is a distance. Part B wants to know what is the marble's speed, so it wants to calculate a final speed. And part C, how long does it take? How long is asking us to calculate a time. So we should notice that it is rolling a new distance. And the old distance on the first roll was 100. So we can write a ratio of distances. It's now rolling 400 centimeters, where before it rolled 100 centimeters, and that is a ratio of 4. It's rolling 4 times the distance. So when it hits the stopper, is it going to be rolling at 4 times the speed? We should also note that the final speed from the last part was 50 centimeters per second. And for part C, we're going to be looking at the time. So the time from the first roll was 4 seconds. So We need an equation with speed and distance in them. The positive physics equations do not have an equation with speed and distance in them. So that's why I'm going to be using the UAM version that has final velocity. Speed and velocity are the same for one-dimensional motion, and displacement works the same way as distance. So I can get rid of this equation, and if I replace v with s, because we're really looking at speed here, speed squared is going to equal 2a. Well, the acceleration is the same, so twice the acceleration is also going to be the same. That is a constant value. And so we see here that we've got a speed squared is equal to a constant times the distance. So that's going to show us that the speed squared is proportional to the distance. We can use that to set up a scaling equation where the ratio of speeds squared is equal to the ratio of distances. Well, we know what this ratio of distances is. That's 4. So if we take the square root of both sides, I get S2 over S1. I'm taking the square root of it, so that undoes the exponent, is equal to the square root of that, the ratio of distances. The ratio of that ratio is 4. So it's not going to take 4, it's not going to have 4 times the speed at the bottom. It's going to have this square root of 4, or 2 times the speed. It's going to be moving twice as fast at the bottom. And now that's just a simple calculation. It hit the stopper at 50 centimeters a second, dropped from the first distance. So that's going to mean that the new speed is twice that, and so that is twice 50 centimeters, or 100 centimeters per second. For the second part, we want to look at the relationship between time and distance. So again, the positive physics equations don't have an equation with distance and time in them. So we're going to use a UAM equation. I can get rid of the term with the initial speed. And here I can say d, distance and displacement are the same thing for one-dimensional, one-direction motion, is equal to, well, 1/2 the acceleration is a constant, times t squared. That's going to imply that we have a relationship between distance and time squared. And again, we can use that to set up a scaling equation. So we have the ratio of distances, which we know to be 4, is going to equal the ratio of time squared. And so again, if we take the square root, we again get the square root of that ratio, and that's going to tell us that t2 over t1 is equal to the square root of 4, so which is 2. So it's going to take twice as much time. It took 4 seconds on the first trial, so it's going to take twice that, and the new time is going to be 2 times 4, or 8 seconds.